Welcome to Yatim Khana and Madrasa, Anjuman Khairul Islam's Pune College of Art, Science and Commerce, Camp Pune 1. Myself, Dr. Arif Tamboli, working as Associate Professor in the Department of Electronic Science. Students, today we are going to study the topic which is called as Time Division Multiplexing and Frequency Division Multiplexing. So, multiplexing technique is used in communication for utilization of a bandwidth, and the bandwidth is a very critical problem in communication. And if you have a small bandwidth and if you want to utilize that bandwidth for many subscribers or for many information signals, in that case multiplexing technique will help you, and today we are going to study that multiplexing. So basically the multiplexing is classified as frequency division multiplexing, wavelength division multiplexing, and time division multiplexing. So for our syllabus, we have a frequency division multiplexing and time division multiplexing. So we are going to focus on these two. Time division multiplexing is further classified into synchronous time division multiplexing and asynchronous time division multiplexing. So asynchronous time division multiplexing is also called as statistical time division multiplexing. So that we are going to study in the next slides. So in this way, this is the multiplexing chart. Now some peoples, they also classified the multiplexing with a little bit different angle, and that also I'll show you. So here in this case, the multiplexing techniques. So this multiplexing is classified as analog and digital. The multiplexing techniques are classified as analog and digital. So in analog multiplexing, frequency division multiplexing and wavelength division multiplexing are there. So in analog multiplexing, frequency division multiplexing and wavelength division multiplexings are there. We are going to study the frequency division multiplexing. And digital multiplexing, the time division multiplexing is there, which is further classified as synchronous time division multiplexing and asynchronous time division multiplexing. Asynchronous is also called as statistical time division multiplexing. So let us proceed for the block diagram of, first of all, we'll start from time division multiplexing, and then we'll understand how the time division multiplexing technique is helping us to utilize the bandwidth of, say, one subscriber. Suppose 4 kilohertz is the bandwidth required for voice channel, then one bandwidth which is having a 4 kilohertz only, and it can be used by many subscribers in time division multiplexing. So let us proceed for that. So this is the block diagram of time division multiplexing block diagram. So observe the block diagram very carefully. We are going to study each and every part of this block diagram. So in this block diagram, this is our focus point, that is called communication channel. And the problem is what? This communication channel is having less bandwidth. This communication channel is having less bandwidth. And now let us consider the example of voice frequency of human being. It is in the range of 300 Hz to 3000 Hz. Therefore, actual bandwidth required for the voice frequency of a human being is 2.7 kilohertz, and allotted bandwidth internationally is 4 kilohertz, little bit on higher side of the requirement to avoid crosstalk, to avoid the crosstalk or interference. So 4 kilohertz is the bandwidth required for voice frequency. And suppose this communication channel is having a bandwidth of only 4 kilohertz, and there are four input signals: input 1, input 2, input 3, input 4. So each input is having a information signal. Each input is having a information signal, and that information signal is nothing but our voice frequency, and it requires 4 kilohertz bandwidth. Therefore, if I want to pass all four information signals on this communication channel, then the requirement will be 16 kilohertz. Requirement will be 16 kilohertz, but I don't have a 16 kilohertz bandwidth. I have a 4 kilohertz bandwidth only, and therefore time division multiplexing logic is used. And what is done in that logic? At a time, only one information signal is passed on that communication channel. The logic is very simple. At a time, only one information out of four information signals, only one information signal is passed on that communication channel. And in this way, effective utilization of that bandwidth is done. And for that purpose, you will require here a multiplexer circuit. So all of you know multiplexer circuit is having many input, one output along with control signal, along with control signal. So we have taken 4 line to 1 line multiplexer, 4 inputs, input number 1, 2, 3, 4, channel 1, 2, 3, 4. Now all of you know very well, this multiplexer will select only one input and passes to the output. But which input is to be selected? It is decided by the status of control signal. It is decided by the status of control signal. Now we have 4 line to 1 line multiplexer. Therefore, our control signals are namely two, control signal 0 and control signal 1. So when both control signals are 0, 0, all of you know input number 1, that is channel number 1, gets connected to the output of multiplexer, and then that input information will get communicated through this communication channel. And when control signal is changed from 0, 0 to 0, 1, then input number 2, mean information signal number 2, will get selected by multiplexer and it comes to the output of multiplexer and then it passes on this communication channel. So in this way, multiplexer will select any one input out of many input, and that is decided by the status of control signal. Two control signal, therefore four probabilities, and that I am going to show you in the next chart. So in this way here, only one information signal is selected by the multiplexer and pass on communication channel. On the right hand side, you see very carefully, there is a demultiplexer circuit. There is a demultiplexer circuit, and demultiplexer circuit is also 1 line to 4 line. 1 line to 4 line, because demultiplexer circuits are having or is having only one input and many outputs. Only one input and many outputs. So here we have selected 1 line to 4 line, means output lines are 4, because on the left hand side our mux is 4 line to 1 line. Therefore here there should be 1 line to 4 line demux. Now when this information signal 1 is selected by the multiplexer on the left hand side, because control signals are 0, 0, and it is passed on communication channel, when it comes to the input of demultiplexer, when that information signal 1 comes to the input of demultiplexer, demultiplexer passes that information signal to any one channel out of 4. Demultiplexer passes that information signal to any one channel out of 4, and that is also decided by the status of control signal of demultiplexer. And therefore you will observe that here, see, synchronization between control signals. Synchronization between control signals is written over here, and when this is 0, 0, this is also 0, 0. Means control signals of multiplexer and demultiplexers are well synchronized. So when control signal of multiplexer is 0, 0, demultiplexer is also 0, 0. Therefore, input which is coming to the demultiplexer will get passed to the output channel number 1, will get passed to the output channel number 1, and therefore output 1 will be your input 1 of the multiplexer. Means information signal number 1 now is passed through the multiplexer going on communication channel, and thereafter it is going to the channel number 1, that is the output of demultiplexer. And in this way, when you change the control signal from 0, 0 to 0, 1, information signal number 2 is selected by the multiplexer and pass on communication channel, and when it is 0, 1, this demultiplexer's control signal is also 0, 1. Therefore that information will get passed to the output channel number 2 of demultiplexer, and therefore output 2 of the demultiplexer is now having information signal number 2, that is input 2 of the multiplexer, and accordingly you can understand. So whatever I have explained here, so in this case here it is explained as shown in above block diagram of TDM. The multiplexer circuit selects any one input according to the status of control signal CS0 and CS1 and passes that input on communication channel. At the end of the communication channel on right hand side, demultiplexer circuit takes this input. At the end of communication channel on right hand side here RHS, demultiplexer circuit here takes this input and passes to the respective output channel according to status of control signal. According to status of control signal, that is CS0 and CS1. Due to synchronization between control signals of multiplexer and demultiplexer, the corresponding input signal on LHS, the corresponding input signal on LHS left hand side gets connected to the corresponding receiver on RHS. Gets connected to the corresponding receiver on RHS, because here the receiver of input signal, information signal number 1 on RHS is the channel number 1, and accordingly the multiplexer circuit works as a transmitter, that is sender, and demultiplexer circuit is working as receiver. Demultiplexer circuit is working as a receiver. It receives the information and passes to the corresponding output channel. Now here the question comes here, for how long time, for how long time the input one will get connected to the communication channel, and who is going to decide that? So here it is a very simple thing. This multiplexer is having two control signals, namely CS0 and CS1. Now as long as both are 0 0, as long as both are 0 0, input number 1 or information signal 1 gets communicated on communication channel and it passes to the respective receiver, that is the output channel number 1 of demultiplexer. Now as long as both control signals are 0 0, control signal of multiplexer as well as demultiplexer, there is proper transmission of information signal from sender to receiver, from sender to receiver. And after some time, when you change the status of control signal from 0 0 to 0 1, the second information signal will go to the corresponding receiver, due to synchronization between control signals of multiplexer and demultiplexer. Now only the question comes, how long time the status of control signal CS0 and CS1 remains 0 0, and on what factor it depends. So here you can understand that these control signals are incremented from 0 0 to 0 1, 1 0 and 1 1. It means if you apply the logic, these two control signals are nothing but the output of 2-bit counter, So now first of all you study uh, this multiplexer, control signal 0, control signal 1. As two control signals are there, there are four probabilities. Both are 0 0. This is 0, this is 1, this is 1, this is 0, and both are 1 1. So if you just look it into this corner, you'll observe that the control signals are incrementing in a systematic manner from 0 0 to 0 1, 1 0 and 1 1. Now, if these control signals are generated by a 2-bit counter, then that 2-bit counter's output will come from 0 0, then increment after applying the clock 0 1, because counter's output will get incremented if and only if you apply the clock. So here the counter 2-bit counter will use, I'll show you that, and that output of counter is incrementing from this level 0 0 to 0 1, then 1 0, but output of counter will increment if and only if you apply the clock. And therefore it is said that how long time the control signal remains in logic 0 0 or 0 1, it depends on clock, that is time period of 2-bit counter, clock or time period of 2-bit counter, and we'll come to that here. See, now you'll understand that our 2-bit counter is there and output of that 2-bit counter is CS0, control signal 0, and control signal 1 intentionally we have taken. Now this 2-bit output counter CS0 and CS1 will increment from 0 0 to 0 1, 1 0 and 1 1. But after how long time the change in the state takes place? After how long time change in the state of control this output of counter means our multiplexer circuit's control signal takes place. So here you see 00 is the initial state. 00 is the initial state of our counter's output. Now, as I told you, output of counter will increment or will change its state if and only if you apply the clock. So here I have given the example of two clocks. And first of all, you try to understand what do you mean by the clock. Clock is nothing but a square wave. Clock is nothing but a square wave. So all of you know in square wave, there is a high voltage level logic 1, low voltage level logic 0. Whenever there is a change in the voltage level from logic 0 to 1, it is indicated by positive edge, that is upgoing arrow. And whenever there is a change in the voltage level from 1 to 0, it is indicated by negative edge, that is downgoing arrow. So this is a positive edge, upgoing arrow, logic 1, downgoing arrow, and then upgoing arrow. And this distance between two adjacent positive edges, is called time period. Now this time you see it is very large. This time is very large. And here one more example is given, positive edge, negative edge, and positive edge. This time is very small. Now let us take into consideration that this time is very small, and therefore when you apply a clock, this type of the clock, to the counter, as this is a square wave automatically generated after this small interval of time, the output of counter will increment from 00 to 01. Means output of counter will change its state from 00 to 01, and therefore here it is given here. See how long time the output status of the 2-bit counter remains in 00. So it remains for the time period t. Then after time period t, this time period t, it is now very small. After time period t, it will go from 00 to 01, and it will remain in 01 again for the next same time, that is time t, for in the 01. And you can show the same, you can repeat the same thing over here again by the arrow, and you can write the t. Means here the output of counter will remain in logic 01 for this time period only t, and thereafter when next positive edge will come, then output of counter will further increment from 01 to 10. And therefore the time period of the clock, that is your 2-bit counter, is very important, which decides how long time the output should remain in a particular status of 00 or 01 or 10 or 11. Now if this type of the clock if you apply, which is having a long time period, you can easily understand that the 00 or 01 or 10 or 11 remains for long time. And therefore when this control signal, this output we are applying as a control signal to the multiplexer, this output of the counter we are applying to the control signal of the multiplexer. Therefore when it remains in suppose 01 state long time, when it remains in 01 state for a long time, then input number 2, information number 2 is communicated on communication channel for long time, and accordingly you can decide the time period. Now the question comes here. See here, as explained above, at a time only one input signal is passed on communication channel. Therefore no crosstalk, because multiplexer selects only one input out of 4 and it passes on communication channel. Therefore no crosstalk in TDM. The time duration of passing the input signal on communication channel depends on the time for which the control signals, that is CS0 and CS1, remains in 00 or 01 or 10 and 11 status. The control signals CS0 and CS1 are generated by 2-bit counter. That is what I explain you. And here the increment in the status of control signal, means from 00 to 01 or from 01 to 10, is controlled by the time period t of clock applied to 2-bit counter, is controlled by the time period t of the clock applied to the counter, this time period t and this time period t. So if it is a very fast incrementing, the time is very small, and this will be slow increment in the output of the counter because time is large. So in this way here it is very clearly mentioned, the increment in the status of control signal is controlled by the time period t of the clock applied to 2-bit counter. If the time period of a clock is suppose 250 millisecond. Suppose if the time period of the clock is 250 millisecond, then in 1 second, each input signal is passed 4 times on communication channel, because 1000 millisecond is equal to 1 second. So we'll take into consideration this time period. Suppose now this time period is very small. This is what, very small, and this is very large. So let us consider this large time period as a 250 millisecond. How much it is? 250 millisecond. And let us consider this small time as only 1 millisecond. Only 1 millisecond. Let us consider this as only 1 millisecond because it is small, and this is a large. Therefore, if you consider 250 millisecond, then here after every 250 millisecond, you will understand, after every 250 millisecond, the output of counter will increment, and finally again it will come back to original status because it is a 2-bit counter. Therefore, you will understand that 1 second is equal to 1000 millisecond. 1 second is equal to 1000 millisecond, and therefore if this time t is 250 millisecond, then 1 second will get divided into 4 parts, and 1 second will get divided into 4 parts, and therefore it is said that in 1 second each information signal is appearing, or each information signal is passed on communication channel. How many times? 4 times. If the time period of the clock is 250 millisecond, then in 1 second, each input signal or each information signal is passed 4 times on communication channel, because 1000 millisecond is equal to 1 second. Now let us talk about another way. If the time period t of the clock is 1 millisecond only, time period t of the clock is 1 millisecond only, means here this time very small. Then in 1 millisecond, if the time period is there, then after every 1 millisecond, try to understand, after every 1 millisecond, the output will increment from 00 to 01, 01 to 10, and accordingly. Therefore, here, in this case of here, if the time period of the t of the clock is 1 millisecond, then in 1 second, each input signal passes 250 times on communication channel. In 1 second, each input signal, that is information signal, is passes how many times? 250 times on communication channel, because time is only 1 millisecond, and increment of the counter is very fast, and 1 millisecond is very less time. The frequency will come to 1 kilohertz. The frequency will come to 1 kilohertz. Therefore 1000 millisecond is equal to 1 second. 1000 millisecond is equal to 1 second. Therefore 250 times each information signal is passed on that communication channel. How many times? 250 times in 1 second. Therefore it is said that, in another way, if you start thinking this communication channel is almost utilized at the same time by all 4 input signals. Almost. This communication channel is almost utilized by the 4 information signals simultaneously. It is almost utilized by 4 input signals. So all 4 are almost appearing on this communication channel simultaneously. And it is observed that the communication which is taking place is very efficient in the sense bandwidth utilization is efficient. We have only 4 kilohertz bandwidth. We have only 4 kilohertz bandwidth, but we are going to use that 4 kilohertz bandwidth for 4 subscriber or for 4 information signal. Actually speaking, for each information signal will require 4 kilohertz, so total 16 kilohertz. But we are using only 4 kilohertz bandwidth and sharing that 4 kilohertz bandwidth in between all 4 subscriber or 4 information signal, and that is what it is said, efficient use of bandwidth or efficient utilization of the bandwidth. And in this way here, this is your time periods adjustment, and now you know that the clock frequencies of the counters are not in kilohertz, it is in hundreds of the kilohertz, and therefore the this rate will also increase. Now let us try to understand this same thing with the another logic. See here, multiplexer, demultiplexer. So here 4 computers, and here again 4 computer. This computer is what sending the information, and this computer is receiving the information. And here output of this computer is called baseband signal, that is the information signal. See here there is a switch S, and here again there is switch S. Now this switch is connected to the computer number 1 on left hand side, and this switch is also connected to the computer 1 on the right hand side. Therefore whatever the information sent by this computer, that will pass on this communication channel, that will pass on this communication channel. And here now the communication is established between the sender computer number 1 and the receiver computer number 1, because switch is at the position number 1 on the right hand side and position number 1 on the left hand side. Now look at this arrow. If you say that this arrow is means switch is thrown to the position number 2, and same way here, if the switch is thrown to the position number 2, then information signal number 2 of computer 2 will pass on communication channel, and it will be received by the receiver computer number 2. It will be received by the receiver computer number 2, because there is a synchronization between this switch and this switch. So this arrow indicates you when this is thrown to the position number 2, it is also thrown to the position number 2. And therefore you see here, when it was at position number 1, the output of the computer number 1 was going on communication channel. When it is at position number 2, the output of computer number 2 is going on this communication channel. When it is at number 3, this will be at also number 3, and on this communication channel, the output information or if information signal of computer 3 will be present on this communication channel. And like that here, 1, 2, 3, 4. In this way, each computer's information signal will pass on the receiving end in this manner, 1, 2, 3, 4. And after that again, the switch will come back to the position number 1. That is counter's output after 1, 1 will come to 0, 0. And in this way here, when it comes to again position number 1, see here this pink color, 1, 2, 3, 4. And then again from 4 it will come here, and then 1, 2, 3, 4. So like that, from this what is to be understood? This communication channel is utilized very efficiently. Sometime information signal number 1 on the left hand side is passed, sometime 2, sometime 3, and sometime 4. And in this way, this is this chain is repeated. This chain is repeated. So it's very simple. And here there is a one more logic, mechanical. It is switch is here and switch is here. So this is conversation A, conversation B, conversation C. Like that, 5 conversations are taken. And here conversation A, B, C, D. So here this conversation B is now passed to the conversation B on the right hand side. And there is a synchronization between this switch and this switch. When it goes to position number 1, this also will go to the position number 1. And now let us study the time division multiplexing. It is basically divided as synchronous time division multiplexing and asynchronous. Asynchronous is also called as statistical. In synchronous time division multiplexing, fixed rotation or on channel. Fixed rotations on channel here. So fixed rotation on channel is there. Here also fixed rotation on channel is there. And in case of earlier whatever we studied, in that case also there is a fixed rotation of channel. Means 0, 0, 0, 1, 1, 1, 1, 0 and 1, 1. So in this way there is a fixed rotation on channel is there in case of synchronous. Now what do we mean by asynchronous? It is more efficient utilization of time slot. How come? See here, first of all let us see synchronous. In synchronous time division, fixed time slot is allotted to each channel. Fixed time slot is allotted to each channel, even though the data oblique information is not available at specific channel. Suppose at one particular channel, suppose channel number 3, information or data is not available, then also specific time slot is available allotted to that channel. But in statistical, it is not like that. In statistical time division multiplexing, the time slots are allotted dynamically. Time slots are dynamically allotted to improve the bandwidth efficiency. To improve the bandwidth efficiency, not bandwidth. Bandwidth is 4 kilohertz only, which is shared by 4 peoples or 4 subscriber or 4 information signal. Now, in statistical time division multiplexing, if any XYZ channel is not having the information or data, then that channel is not allotted a time slot, and that channel is skipped, and next time channel is searched, and that is called dynamic. That is called dynamic. In statistical multiplexing, the number of slots in each time frame is less than the number of input lines, and this will happen if and only if there is no data or information and at one particular channel. If there is information and data at all four channel, this will not happen. So that is it is to be understood here. The multiplexer checks each input line in round robin fashion. It allocates a slot for an input line if the line has the data to send. It allocates a slot for an input line if the line has the data to send. Otherwise, it skips the line and checks the next line. That is why it is said statistical. That is why it is said statistical or asynchronous, or what? Asynchronous. So in this way, time division multiplexing is used to share only one bandwidth by many subscribers, you say, or by many information channels accordingly. Now we'll proceed for the next logic, which is called frequency division multiplexing. The next logic is what? Frequency division multiplexing. So as the name suggests, frequency division multiplexing, in this case a specific carrier frequency in this case a specific carrier frequency is allotted to each information signal. Specific carrier frequency is allotted to each information signal. One thing you have to remember, time division multiplexing is preferably used for digital communication, and frequency division multiplexing is preferably used for analog communication. So here, in this case, now suppose here your signal number 1, that is information signal number 1, is present at channel number 1. So in FDM, what is done? In FDM, frequency division multiplexing, this information signal number 1 is modulated with a carrier frequency of 64 kilohertz. Is modulated with a carrier frequency of 64 kilohertz, and modulated output will be here. Now there is one more information signal 2. There is one more information signal 2, and in FDM, the information signal number 2 is further modulated with the help of modulator number 2, but the carrier frequency of this second modulator is not same 64, it is different, and it is 68 kilohertz. So there is a 4 kilohertz difference. It is a 68 kilohertz. Now suppose information signal number 3 is there, then in FDM again signal number 3 is further modulated with modulator number 3, and the carrier frequency of that modulator number 3 is now 68 plus 4 is equal to 72 kilohertz. And therefore here in FDM, each information signal is assigned a different carrier frequency. Each information signal is given a different carrier frequency. Therefore, modulated output of every information signal is having different shape, and like that here you'll come to know from modulator number 1 to modulator number 2. For modulator number 2, the carrier frequency will be 108 kilohertz. If you just go and adding the 4 kilohertz in 72, then it will be 76, and then it will be 80, then 84, and accordingly it will be 108 kilohertz. Now in FDM, 12 subscribers are combined together. 12 subscribers are combined together, and it is called a group. That we'll understand in the next slide. And all that modulated outputs, because each information signal is modulated with a different carrier, and all that modulated outputs are given to a mixer, and all that modulated outputs are passed on communication channel. And this is important here. In frequency division multiplexing, simultaneously all 12 communication channels are passed, all 12 information signals are passed on communication channel after modulation. I will repeat once again. In frequency division multiplexing, all 12 information signals, are passed on communication channel after modulation. And when modulation is done, each information signal is modulated with different carrier, Therefore, the mixing or the interference of modulated output. Therefore, the mixing or the interference of modulated output will not take place. Will not take place. But if you don't perform the modulation and if you pass the information signal as it is on to the mixer, all information will get mixed up with each other. And therefore, the modulation is very much important in FDM. Modulation is very much important in FDM. Separate carrier is allotted for every information signal. And there is a gap of how much? 4 kilohertz. Now let us try to understand this. So here a group consists of 12 channel and bandwidth will be how much? 48 kilohertz, because one voice frequency or one information signal of voice frequency requires 4 kilohertz bandwidth. And like that, the group consists of 12 channel in FDM and the bandwidth required is 48 kilohertz. Now let us come here. Whatever I said, it is given here. As shown in above block diagram of FDM, each information signal is modulated with different carrier frequency. For example, signal number 1 is modulated with carrier frequency of 64 kilohertz. Signal number 2 is modulated with carrier frequency of 68 kilohertz, and accordingly the difference in carrier frequency is of 4 kilohertz is maintained. Now let us understand very clearly with the help of this block diagram. Information signal 1, information signal 2, information signal 3, which is also called baseband analog signal. You have three information signal and these three information signals are different. Means somebody is speaking suppose in Hindi, somebody is speaking English, somebody is speaking in Marathi. Now what you are doing, the logic here, see, information signal 1, you are modulating with modulator 1 with carrier F1. With carrier F1, see the carrier. This is the carrier, 64 kilohertz carrier. Now information number 2, signal number 2 is modulated with modulator second and carrier is F2. Carrier is F2. F2 is how much? 68 kilohertz. Therefore time is less. Here frequency is less, time is more. Frequency is increased, time is less. Now carrier number 3. Carrier number 3, modulator number 3 is a carrier frequency of 3. How much? 68 plus 4, 72 kilohertz. And this information number 3rd is modulated with carrier 72 kilohertz. Therefore, you see here very carefully, the output of modulator 1 is different shape. The output of modulator 2 is different shape. The output of modulator 3 is different shape. Why? Because each signal is modulated with different carrier, and therefore output of all modulator circuits will be different, and when they combine here, they are not going to interfere with each other. There is no crosstalk because each information signal is modulated with different carrier, and therefore even though it is a mixer, because of different carrier, the frequencies will not get mixed to each other, and these are having separate identities. Now here on the receiving end, what will happen here? See, on the receiving end, and now here you will understand that now on this communication channel, if all three information signals are going, then you'll immediately understand that the bandwidth will be proportional to three subscriber or three information signal. All three information signal, of course, after modulation are passed on communication channel, but simultaneously all three are going. Therefore, the bandwidth in FDM is required is more, and it is proportional to number of information signals. Now, when this information signal goes on that side, what will happen? We'll see here. Now here, due to modulation of information signal with different carrier frequencies, the output of each modulator circuit is different. Here see, output of each modulator circuit is different, and when these signals are given to a mixer and pass on communication channel simultaneously, at that time interference into bracket crosstalk does not take place. Interference or crosstalk does not take place because the credit goes to what? The credit goes to, yes, modulator circuit. Different carrier frequencies are allotted, therefore this is happening. The communication simultaneously, at that time interference or crosstalk does not take place. Now on communication channel, when it goes on the other side, you'll understand now. Let us come here. Yes, so here if you come to this side, then what? All three informations are here, but all three different informations are modulated with different carrier. Suppose Suppose means actually first signal is modulated with 64 kilohertz carrier, second signal is modulated with 68 kilohertz carrier, third signal is modulated with 72 kilohertz carrier, and when it comes here, see, this is very important now. On the receiving end, on the receiving end, there are three filters. There are three filters: filter 1, filter 2, filter 3. Now this signal, which is a combination of all these three, is applied simultaneously to all these three filters. This input signal, which is combination of all these three, modulated output of all these three, is applied simultaneously to all these filter, and therefore here this filter is very important. It is a frequency filter. It is a frequency filter. So frequency filter number one, upper side, will only take 64 kilohertz carrier, will only take 64 kilohertz carrier, and all other means 68 kilohertz and 72 kilohertz will be rejected by this filter. And therefore this is a frequency filter is designed such that this frequency filter will select only 64 kilohertz carrier, and it will come here. And thereafter what is to be done here? This is modulated output. This is modulated output filter by this circuit means selected by this filter circuit. Now this has to be demodulated. This has to be demodulated such that carrier and information signals are separated. Such that carrier and information signals are separated. There is a demodulator, and see here this demodulator, what it is doing? It is separating the carrier F1. It is separating the carrier F1 and information signal. Separating the carrier F1 and information signal. And in this way here, this carrier F1 was what? This carrier F1 you see here, this was the carrier, and this was the modulated output. So after filter, this modulated output comes here at the receiving end. At the receiving end, after filter, the same modulated output come, because this frequency filter only pass 64 kilohertz modulated output. And in this way here, next filter now. The next filter is of 68 kilohertz. How much kilohertz? 68 kilohertz. Therefore, it will only pass the carrier of 68 kilohertz, or it will only pass the modulated output is consist carrier only. It will only pass the modulated output of 68 kilohertz and reject all others, and in this way here, this is the second input information which is over here. You can understand, see here, and filter is doing a very fantastic job, you can say, taking that much carrier frequency only and rejecting other. And in this way, third filter will only take the carrier of 72 kilohertz and reject 64 kilohertz as well as 68 kilohertz. And this demodulator circuit will separate the carrier of 72 kilohertz and information signal. And final information signal will come here. So here it is clearly given at the receiving end on RHS, when all modulated signals with different carrier frequencies are applied simultaneously to all frequency filter. Simultaneously to all frequency filter. The frequency filters are designed such that they will only pass either 64 kilohertz, 68 kilohertz, etc. and reject other frequencies Filter 1 is only passing 64 kilohertz carrier or modulated output and are rejecting others, and accordingly the output of frequency filter is carrier frequency. The output of frequency filter is carrier frequency, that is modulated output is carrier frequency, and it is demodulated such that carrier signal and information signal are separated. Carrier signal and information signal are separated. See this demodulator separating the carrier and information is coming to the output, and in this way here demodulator such that carrier signal and information signals are separated. Therefore in FDM synchronization is not required. In FDM synchronization is not required, but frequency filters are required. Frequency filters are required. No synchronization, because each filter is getting all frequencies, all carrier frequencies, but filters are designed accordingly. Now the combination of 12 signal means 12 information signal, that is called subscriber also in communication language. 12 subscriber means 12 information signals. The combination of 12 signal is called a group. is called a group. If the information signal is a voice frequency, then required bandwidth is 2.7 kilohertz. If the information signal is a voice frequency, then required bandwidth is 2.7 kilohertz, but allotted bandwidth is 4 kilohertz to each information signal. And it is internationally decided the allotted bandwidth is on higher side than the requirement, to avoid the interference. Now, why the bandwidth is 2.7 kilohertz? Because voice frequency is 300 hertz to 3000 hertz. So if you subtracted upper frequency from lower frequency, it will come 2700 hertz, means 2.7 kilohertz. Therefore, the bandwidth required for one group of 12 signal is 48 kilohertz, because each information signal is allotted the bandwidth of 4 kilohertz. And like that here, in case of this, again here, this demodulation circuit, modulation circuit, carrier is F1, carrier F2, carrier F3, and modulated output here. Then it comes to communication channel. Filters are performing their job and selecting that much frequency of the carrier, which is what here. And then this is going, demodulator is separating the carrier and information signal. And in this way, information will come here. See, this information exactly is here. This information is exactly here. This information is exactly here. Here modulation is done with different carrier. Here demodulation is done and carriers are separated. One more diagram is there. You can just watch this diagram and understand in the same manner. Carrier F1, carrier F2, carrier F3, modulated output different shapes and going like that. Three information signal, Marathi, Hindi, English, you can say. On the receiving side, all that three carriers are applied simultaneously to all filter, but filter performs their job. This will only allowed 64 kilohertz carrier, and this is the modulated output of the information number one. And then this is demodulator separating carrier and information. And in this way, you can stop this slide, you can watch, and you can understand that, see, same information read is over here, same information read is over here, same information read is over here. So this same information is passed over here. And here in FDM, now what is the problems here? The problem is in FDM, all information signals after modulation, all information signals after modulation are passed on same communication channel, simultaneously. But interference will not occur because each information is modulated with different carrier. That is most important. Each information is modulated with different carrier. 64 kilohertz is one carrier, 68 kilohertz is another carrier. Now here you see, again there is a gap of 4 kilohertz in every carrier. In spite of what? In spite of there is already excess bandwidth allotted for information signal. Excess bandwidth allotted means what? Required is 2.7 kilohertz. Allotted is 4 kilohertz. And further more care is taken to avoid the interference. Therefore, it is said that here interference will not take place due to different carrier allocation. But unfortunately, if you allot the same carrier, to the two information signal, then crosstalk will take place. And here, therefore, it is said here it is a bandwidth hungry or bandwidth thirsty. It requires more bandwidth because all information signals after modulation comes on the communication channel. So here it is given that here voice signal is number one, bandwidth required 0 to 4 kilohertz. 4 kilohertz is the bandwidth. This is the range, bandwidth range. And like that you can easily understand group, how many subscriber or how many information channel? 12. One channel require 4 kilohertz. So 12 into 4, 48 kilohertz. So you stop this slide, you watch this and you will understand that. So there is a voice signal, 12 voice signals. If you combine together, there is a group. Then if you combine five groups to each other, how many? Five groups in one module, then it is called super group. And that you will understand in the next slide. See here. So how to read this, I'll tell you. This is a group. So come to here. This is a group. 48 kilohertz is the bandwidth of group. Why? Because 12 voice channels are there. 48 kilohertz is the bandwidth of group because 12 voice channels are there. Each voice channel requires 4 kilohertz bandwidth. Therefore, 4 into 12 will be 48 kilohertz. And see here, 12 channels, 12 voice channels, vertical. 12 wise channels, 1, 2, dot, 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 12. 12 wise channels combining together forms a group. Forms a group. Now directly come here, super group. What is a super group? Super group consists 60 wise channel. How many wise channel? 60 wise channels. 60 wise channel means how many groups? 5 groups. Because in one group there are 12 wise channels. So 5 groups. So here you see 5 groups. So 60 wise channel. Each wise channel requires how much bandwidth? 4 kilohertz. So 60 into 4 will be 240 kilohertz is the bandwidth of super group. Is the bandwidth of super group. Then directly come here master group. What is a master group? Try to understand this. 600 wise channels. How many? 600 wise channels in a master group. Now 600 wise channels in a master group means one bandwidth, one channel will require 4 kilohertz. So 600 into 4 you do accordingly, you will get the answer. And here they see 10 super groups. How many? 10 super groups because in one super group, how many groups are there? 5 groups. And in one group, how many channels, how many information signals are there? 12. So accordingly, here 10 super groups will form is master group. 10 super group will form a master group, and finally you come to the jumbo group. The jumbo group consists of 6 master group. The jumbo group consists of 6 master group, and therefore it is said that here carrier must be different. For every information signal, carrier must be different, and you can see here how many wise channels? 3600 wise channel. In what? Jumbo group. In a jumbo group, 3600 wise channel means 3600 information signals in a jumbo group. Therefore, definitely you will try to understand that there will be 3600 carrier frequencies. There will be 3600 different carrier frequencies. And unfortunately, out of that 3600 wise channels, if any two wise channel get same wise frequency allotted, if any two wise channels get same carrier frequency allotted, if any two wise channel get same carrier frequency allotted, then crosstalk will happen. And in this way, here applications of FDM, you read it in telephone system, amplitude modulation, frequency modulation, radio broadcasting, television broadcasting, sound and video. Video signal bandwidth is 5 megahertz. Video signal bandwidth is 5 megahertz standard. First generation cellular phone was used. Nowadays it is not using FDM by cell phone. Then applications of FDM. Very common application of FDM in AM and FM. AM means amplitude modulation, FM means frequency modulation, radio broadcasting. Special band from 530 to 1700 kilohertz is assigned to AM radio. This is standard. Each AM radio station needs 10 kilohertz bandwidth. Now FM, all of you know, you are listening FM radio. It is from 88 megahertz to 108 megahertz. And in every city, if you go to Pune or if you go to Mumbai, if you go to Delhi, there is the same this, but radio stations are driven by the separate authorities. So that channel is what purchased by the different authorities in different cities. And like that here, it is 88 megahertz to 18 megahertz, 108 megahertz FM, and therefore it is said that FM station requires the bandwidth of 20 kilohertz. So that we'll see later on. All radio stations need to share this band. Each station uses different carrier frequency, which means it is shifting its signal and multiplexing. So now, if you talk about radio, you can tune the radio to different radio stations. To different radio stations. Tuning the radio to different radio station means what? Tuning the radio to different radio station means catching the particular carrier frequency of that radio station. Catching the particular carrier frequency of that radio station, and your radio is doing the job of demodulation. Your radio is doing the job of demodulation. It catches that carrier frequency, and then there is a demodulator which separates carrier and information, Therefore, see here, the receiver receives all these signal, but receiver selects only one by proper tuning. And there are now differences between time division multiplexing and frequency division multiplexing. So first difference is very simple. TDM means time division multiplexing, FDM means frequency division multiplexing. Each channel is allotted a fixed time slot. In time division multiplexing, each channel is allotted a fixed time slot. In FDM, each channel is allotted a fixed carrier frequency. Each channel is allotted a what? Fixed carrier frequency means, in another language, each channel is modulated with different carrier, In TDM, only one channel occupies entire bandwidth of channel. Channel means information signal. Only one information signal occupies the entire bandwidth of channel. Only one information signal occupies the entire bandwidth of channel, means only one information signal is allowed to go on that particular channel, because multiplexer selects only one. Now here each channel is allotted a fixed carrier frequency. Here, sorry, all channels occupies the bandwidth of channel, means all information signals. Channel means information signal. Why it is channel given? Because in multiplexer there was a channel 1, channel 2, channel 3, like that. And here each channel means each information signal, or all channels are here occupies the bandwidth of channel. So here bandwidth is required more. Crosstalk does not occur because only one channel, that is information signal, is allowed to occupy the entire channel or to go on that communication line. Crosstalk may occur, if same carrier is allotted, if same carrier frequencies gets allotted to a particular channel, to a particular information channel. Then here it requires less bandwidth, because we have managed 4 kilohertz bandwidth by 4 people. You can also manage the 4 kilohertz bandwidth by 8 people or 16 people or 32 people also, because the multiplexers control signals are driven in 100 of the kilohertz, So here bandwidth required is more. Synchronization between mux as a transmitter and demux as a receiver is required. Synchronization is not required, but filters are required. Synchronization is not required, but frequency filters are required. It is preferred for digital signal, and it is preferred for analog signal. And in this way, you can stop the slide and you can watch the information again and again and read the information again and again. Now this is a one more slide for communication channels. There it is said that there are guided communication channel and unguided communication channel. Guided means with wire. That wire may be twisted pair wire, coaxial cable made from metals only. Twisted pair is made from metal, coaxial is made from metal, or optic fiber cable which is not made from metal, it is made from glass or special fiber. So it is a guided. And unguided means what? Unguided means, here see, terrestrial, microwave and satellite microwave and broadcast radio. All these are electromagnetic waves, or these are electromagnetic waves with different wavelength. And in this way, I will conclude that today we have completed the topic which is called time division multiplexing and frequency division multiplexing. So a very important thing is, in time division multiplexing, a less bandwidth of 4 kilohertz only is shared by 4 subscriber or 8 subscriber or 16 subscriber or 32 subscriber. And in time division multiplexing, only one information signal is passed on that communication channel. So at a time, only one information is going on that communication channel, therefore there is no crosstalk. In frequency division multiplexing also, each information signal is modulated with different carrier, and therefore there is no crosstalk. But unfortunately, in a suppose in a jumbo group, and there are so many information signals, and if unfortunately carrier frequency same carrier frequency is allotted to the two different information signal, then crosstalk may occur. And these are the very basics of the communication. You watch the slide. Thank you very much for watching the video, and we'll see in the next lecture for the next topic.